Good afternoon, everyone. Thank you so much for joining us. My name is Katie Poser. I'm the Outreach Librarian for the NOAA Central Library, and we're very excited to bring today's seminar to you. I would like to welcome Ryan Kramer to our talk today, linking models and observations to understand and project climate change. Ryan is a scientist at NOAA's Geophysical Fluid Dynamics Laboratory, or GFDL, in Princeton, New Jersey. Using climate models and observations to study Earth's changing energy budget. He will be serving as OAR's liaison on climate modeling and climate observations, working to build some new collaborations between these two NOAA communities, OAR and the lab. So, Ryan, I will let you take it away.
Great. Thanks so much, everybody, for coming out to join. And thanks, Katie, for the intro and this really cool opportunity to sort of introduce myself. I'm actually quite new to NOAA. I joined in the beginning of June, mainly to do research on my bread and butter, which is Earth radiation energy budget and trying to understand how changes in the energy system of the planet drive climate change. It's really one of the core fundamental drivers of climate change. And along with that, I am also going to think more broadly about how GFDL and OAR more widely can use observations for climate research and climate modeling. And we'll be starting this new liaison position working largely from Silver Spring in Maryland. So if you're in the area, I'd love to meet you. And my goal is to use the position to hopefully build stronger collaborations and communication between the climate modeling community at NOAA and the observational community, and make sure that the relationship is really mutually beneficial to both. And I think it's an exciting time for a position like that. The climate modeling is leaning towards simulations where we can take action, shorter time scales where we can really take action based on our simulations, but also validate them with the unprecedented record of observations we have now, a couple of decades worth, at least in the satellite era, for example. And so, yeah, I think that it's an interesting time for climate modeling and how that community interacts with observations. And I'll say that we use observations throughout climate model development and throughout climate research, but the relationship to observations and, say, climate modeling is different and arguably maybe less intertwined than the relationship between weather modeling and observations. We don't have, at least traditionally, a big data assimilation system within our climate models. It's really more down to the individual scientist level, looking at the data themselves, doing basic research, and using that kind of as a basis for developing the climate model. So hopefully during this talk, I'll give you a sense of my work and also just more broadly how the climate modeling community uses observations and where I think those kind of trends will go into the future. So as Katie nicely mentioned, in addition to this liaison role, let me see, it starts to click through, one second. I also work with the Geophysical Fluid Dynamics Lab. GFDL is my home base. It's in Princeton, New Jersey, for those unfamiliar, and it's really, I believe, the largest concentration in NOAA of climate science research and climate modeling. And it's a great place to do it. GFDL is really, in a lot of ways, sort of the home and the birthplace of climate modeling. So going back all the way to the 1960s and even before. On the left is a classic plot from Manabe and Weatherald. Suki Manabe was at Princeton and GFDL and recently won the Nobel Prize in part for this plot, honestly, in this paper. And this is it's kind of the beginnings. It's a simple one-dimensional radiative convective equilibrium model with the very basics of climate change and climate processes included. But despite this simplicity, Manabe was able to represent and simulate processes that today are core to our understanding of climate change. and core to seeing the effects of climate change in our observations. So the different vertical lines here are climates with different CO2 concentrations. And you can see sort of at the bottom of the profile near the surface here, the different CO2 concentrations lead to different surface temperatures. You can make that out a little bit, but even more prominent and honestly even more remarkable that they were able to simulate this is the fact that different CO2 concentrations lead to different temperatures in the stratosphere. The more CO2 you have, the cooler the stratosphere. And this is exactly what we see in our observations today. On the right is a plot of trends in temperature by latitude on the x-axis and vertical level on the y-axis from microwave satellite instruments. And you can see that with increasing CO2, you get the warming near the surface that I think we're all familiar with. But warming can happen for other reasons as well. What makes this distinctively caused by large increases in CO2 is the cooling that we see in the upper atmosphere, in the stratosphere, which Manabe was able to represent all those decades ago. So as you can imagine, climate modeling at GFDL and elsewhere has become much more detailed and complex and comprehensive than a simple 1D model simulation, but, and I'll get into that a bit more detail throughout the talk. And so I'll just say also, before I joined NOAA in June, I was at NASA's Goddard Space Flight Center in Greenbelt, Maryland, studying similar topics, Earth radiation budget and climate change, but I really got my hands dirty and really got to understand satellite data and its usefulness for understanding the climate. So on the right there, you can see the current fleet of NASA satellites that are observing Earth and useful for climate change. You can see Cygnus going around across North America, which is useful for monitoring hurricanes, and going from the south to the north right now is Calypso and CloudSat, which I use a lot which measures clouds. And there's just it runs the gamut: precipitation measurements, soil moisture, and it's all useful for climate research and climate modeling because the climate system is complex. It has all these different components and they all intertwine and impact things that we really care about. The one sort of saving grace maybe in climate science is, despite all this complexity, the fundamental drivers of climate change is really kind of well understood and in some ways straightforward to understand. Really, climate change is about energy balance in the climate system. When the amount of energy coming into the system from the sun is equal to the amount of going out, which is mostly in the form of thermal radiation, infrared radiation. When those things are in balance, your climate is stable, right? But when something throws off that balance, like increases in greenhouse gases, the climate changes in response until you reach a new equilibrium. And so looking at this kind of in a bit more detail, you can see the solar radiation from the sun coming in, a fraction of it gets absorbed in the system, but a lot of it, a fraction of it gets reflected back out to space, off of clouds, for example. And then on the right in red is thermal emissions out to space, our main source of energy escaping out and bouncing what's coming in. Anything with a temperature emits this thermal heat energy. And along the way, some of it gets absorbed and stays in the atmospheric system by clouds, for example, some of it natural like clouds. And this is what makes the planet livable. We need some of this, so not all the energy escapes and we all freeze, right? But the non-natural part is that as humans emit certain gases, greenhouse gases, like carbon dioxide, this traps more heat and more of it stays in the system, heating the planet. And that's really kind of what comprises what I research and really what drives climate change on sort of a fundamental level. And so you can see kind of that represented here, the thermal energy being trapped as it tries to escape, being trapped by pollution, for example, in the form of carbon. But of course, we're not just emitting from one factory or one car. We're emitting throughout the globe, and quickly things become well mixed. This is a nice simulation of emissions of CO2 throughout the Earth. Most of it, of course, occurring in the Northern Hemisphere, where most of our pollution, most of our industry occurs, but quickly CO2 becomes well mixed. And we see over time, globally averaged, that since the Industrial Revolution, there's been clear increases in key greenhouse gases, right? This is something I'm sure you're all familiar with. Rising CO2 shown in blue, methane in orange there in yellow, and N2O as well in green. And this has coincided with clear increases in our observation of surface temperature. Also, since the Industrial Revolution, we've seen these clear increases. And these are perfectly important and clear signals of climate change in our observations, but I make the case that what really links the two, what connects those greenhouse gases to the climate and to the rising temperatures, is Earth's energy budget, and radiation budget. And fortunately, we measure that too. This has been going on for decades, but most prominently and maybe and most recently, NASA's Clouds and Earth Radiation Energy System series instruments have been flying around the globe, measuring reflected solar radiation from the planet back out to space, and measuring the amount of outgoing thermal long-wave radiation as well. And that combined with measurements of incoming solar radiation, shown at the top left, we're able to diagnose the net energy balance at the bottom right, the difference between the absorbed and outgoing energy. And you can see most of the energy being concentrated in the tropics, where we have the most heat, and the seasonal cycles too, as those globes spin around. But what's not really apparent from this kind of local, spatially resolved perspective is any trends, right? What's happening over the long term. But if we average that series record globally, what we find is that there's this really clear positive trend in the top of atmosphere energy imbalance. Positive here meaning more energy uptake over time, more heating of the planet. And so the series measurements are shown in orange, and in blue are independent measures of planetary heat uptake, mostly based on ocean heat content measurements, and they agree really nicely. And this isn't a surprise. Most of that extra heat due to the imbalance in energy at the top of the atmosphere actually goes towards heating the oceans. And so that's maybe one distinction between thinking about climate and thinking about kind of shorter term weather scales is that we really care about what happens in the ocean in terms of heat storage, distribution of heat throughout the climate system, and how it feeds back onto the atmosphere. And once that energy starts going into the ocean, as well as the land and ice and into the atmosphere, we start to see the climate impacts that we all really directly care about. In our observations from satellites, we can see the evidence of rising sea levels. As the oceans heat up, they naturally expand. We've seen sea level rise of over 100 millimeters since the 1990s. And sea level rise, for those in the DC area where I am, is one of our key climate concerns. Those of you that have been to the tidal basin in the National Mall may have been there during flooding, even on a sunny day, as those rivers in DC are tied closely to the ocean tides and rising sea levels. That heat can also go to melting the ice. These are measurements from GRACE and GRACE follow-on satellite missions, which is designed to measure gravity, but scientists have found a way to use it to measure mass changes on the Earth, for example, in the form of ice. And we see, from grace to clear declines in ice mass over Antarctic and Greenland as well. Heat goes towards causing droughts, for example. The imbalance goes towards causing droughts in the western US. On the top left is satellite measurements of soil moisture. And the heat's gone towards proliferation of wildfires. On the bottom right there is kind of a neat image of wildfire intensity, mostly from MODIS satellite, and you can see various hot spots lighting up across the planet. And so, you know, we really kind of are in this golden age of observations, especially with satellites, that really let us monitor climate, but also understand the processes that drive it. And that's really ultimately what's important for developing climate models. And the other takeaway is that climate science has a lot of components, right? We care about land processes and soil moisture. We care about fires, ice dynamics. We care about the biosphere. Vegetation, for example, can regulate the amount of carbon in the atmosphere. It can also affect temperatures near the surface and moisture through evapotranspiration. Precipitation starts to play a role. We care about the gases in the atmosphere as they absorb energy. We care about aerosols that reflect out to space. And so you can imagine that what we kind of consider climate science requires a lot of expertise from different fields. And that's how we sort of view climate modeling today. That climate modeling has sort of incorporated and encompassed over the decades more and more of these different fields over time. We started in the 50s and 60s with basic simulations of just the atmosphere and land surface. A bit after that, we started thinking about the oceans and more deeply bringing in things like atmospheric chemistry and the representation of the carbon cycle. As we move into the 80s and 90s, we start thinking about things like ice sheets and how to represent them, and more recently, interactive vegetation. Until what we have today, we don't call them just climate models, but we have Earth system models that try and simulate all these components as best as possible to get as complete representation of the climate as we can. And so with all these components and all these complexities, we split up the globe when we do our climate modeling into individual grids, both resolved spatially and at different vertical levels, and try to simulate all these processes and use our observations and our knowledge to develop equations that simulate these different processes in our climate models. And as you can imagine, it's complex, right? A lot of different components to all of this, a lot of things that we just don't quite know yet. Things like the impact of vegetation phenology. We're starting to understand, it's also starting to observe, but just at the beginnings of how we can incorporate it into our climate models. And, you know, a lot of different components, but despite this complexity, climate models are actually pretty good at simulating the climate. We can continuously testing our models against the observed historical period. And really for decades, we've seen climate models being able to observe trends over the observed period. Shown here in the top row is the models versus observations, trends in temperature at the surface over a bunch of different periods, going all the way back to Manabe's work in the 1970s. In the bottom row is a metric of temperature after a doubling of CO2, kind of inferred from the shorter time periods. And we do see consistently some nice general agreement between the models in red and the observations in blue. And in cases where there may be some clear disagreement, a lot of times that's because we didn't properly tell the model what we didn't have the proper inputs into the climate model to tell them some basic facts about the climate system, how much CO2 is in the atmosphere, so on and so forth. So, that all being said, that's only really obviously only half the picture. We use climate models to simulate really long timescales, and so it's great that we can observe the present day and the recent past. But the question, of course, is how well are we simulating the future? And as we head into the future, things obviously become much more uncertain. So shown here are some kind of key variables that we care about as climate modelers and also society cares about. Global mean surface temperature at the top left, ocean heat content at the top right, Arctic sea ice in September at the bottom left, and global land precipitation at the bottom right there. And again, what we see here is the simulations of the past in black and uncertainty around that in the gray shading, and then observations of the green line. We see generally good agreement, even over shorter time periods. But as you extend out, we see kind of the envelope of uncertainty grow over time until we get to the approaching 2010. And there's, as you can imagine, a lot of reasons for this uncertainty. But I think one thing worth pointing out is that with climate modelings, we're not necessarily predicting, we're really more so projecting. And the distinction there is we're not always saying this is exactly what's going to happen, right? I mean, people will ask us how much warming we're going to get in 50 years, how much the seas are going to rise in 50 years. We're not really trying to answer that directly necessarily, at least kind of with the basics of climate model. What we're trying to answer is what will happen given a certain scenario, right? And that really also accounts for some of the uncertainty as well. We don't know what people are going to do, right? So you can really think of kind of three types of uncertainty with climate modeling, kind of nicely shown here. In orange is uncertainty associated with internal variability, right? The chaotic nature of the system. In blue is the inherent uncertainty of the climate model itself, processes that we don't fully understand how to represent or that we can't quite resolve yet, different representations across different models. But in green is that uncertainty in what will happen to society in a way, right? Will we continue to ramp up our emissions of greenhouse gases? In that case, you may be towards the top of the green envelope, leading to strong temperature increases by 2100. Or maybe we'll take drastic action to reduce our emissions and the warming will level off. And then maybe we'll eventually find ways to remove greenhouse gases from the atmosphere and start to see a cooling over time. So, we really try to grapple with all these forms of uncertainty and make sure that we're simulating and trying to project for all the possible realistic scenarios that we may head towards. For the rest of the talk, though, I'm going to focus a bit more on sort of the blue component, the true uncertainties in the climate model itself, and try to explain how we use observations to build the models, evaluate the models, and think about this uncertainty. And a lot of the uncertainty comes from the fact that climate occurs on a lot of different scales, right? We can go all the way to the 100,000 plus kilometer scale where we care about things like large scale ocean circulation and so carbon interactions, 1,000-kilometer scale where things like vegetation dynamics and ENSO come into play. And right now, most climate models that we run out for long-term simulations, we're running at about 25 to 100-kilometer scale. And so we're able to explicitly resolve things like ocean tides and coastal upwelling and directly have ENSO in our simulations, but there's a lot at smaller scales that we don't directly represent yet, and I'll start to get into that in a bit more detail later on in the talk. Things like mesoscale circulations at the kilometer scale. Now, a kilometer is about what we're kind of as a community striving for at this point. But even beyond that, at the smaller scale, there's even finer processes that are really fundamental to our understanding of the climate and our ability to accurately simulate it. Things like vertical mixing and convection and microphysical processes that determine how clouds form and how they grow and eventually disappear. And as I kind of alluded to, there's been this steady march of increasing the resolution of climate models over time as our computational power has increased. And as we increase that resolution, we can start to resolve more of these processes. So these different schematics here are basically the average vertical resolution for different IPCC, the models that went into the different IPCC assessment reports over the years, which are spaced out about every 7 years or so, starting from FAR, the first assessment report, where the models were about 500-kilometer grid spacing, to AR4, where they were about 100 kilometers or 1 degree. And now at GFDL and elsewhere throughout climate modeling centers around the globe, we're thinking about single-digit kilometer scales. GFDL, we have X-Shield, which is running at 3-kilometer scale. We consider a global storm resolving simulation. On the right is a pretty cool image of a group in Germany ran their model at 1-kilometer resolution, trying as best as possible to simulate the globe on the left, which is the image of the famous image of the blue marble taken in the 1970s from space. And it's pretty impressive. They capture a lot of features. If you stare at it long enough, you'll see some kind of unrealistic things. But it's kind of a beautiful image about where the climate modeling is heading and the scales we're able to resolve on. But the catch is these simulations that they ran to generate these beautiful images they were only able to run them for, I think, a handful of days. We start to hit these limits of computational power, and I think that's maybe another distinction between climate modeling and the weather. I think probably those of you in the weather community say, 5, 10, 15 kilometers. We've been kind of at that for a while, 20 kilometers. But for climate modeling, once you couple the ocean and all these other different processes that matter on these longer time scales, and then once you start doing these simulations for hundreds of thousands of years, the expense really starts to add up computationally. But all this matters. It's important to strive for, because at the end of the day, what we really care about and what we really want to resolve are the local processes, right? I mean, maybe with a kind of a coarser resolution model, we can get the basic picture on the left, which is showing that at different levels of global warming, you get increasingly more intense heat events as we project. So with 4 degrees Celsius of global warming, imagine taking your hottest day you've experienced and then adding 5 or 6 degrees on top of it. Maybe we can get that picture generally with the models we have today. But on the right is a heat map of DC, for an extreme heat day, and there's some really clear spatial structure to that heat that really matters, right? We see over DC that the hottest sections in orange tend to be in our poorest communities in DC, in contrast to somewhere like Northwest DC over Rock Creek Park, where the temperature was a bit cooler. And you can imagine the city needing this to figure out how to distribute resources and set up heating and cooling stations throughout the city. And so, kind of as we strive to get down to these sorts of resolutions, there's sort of a growing demand to test our models and evaluate our models with more and more observations. at these local scales. And so kind of for the next talk, I'll talk a bit more about specifically how we use those observations to build our climate models really throughout the entire process. So I think of really three sort of core steps to developing our climate models. I'll go through just briefly here and kind of get into some of the details, but you start with sort of developing the core of your model, basic equations of how motion occurs and some of the input variables we need. And we at some resolutions we can simulate certain processes, but we can't simulate all of them. So we develop these parameterizations shown in the bottom right there to represent the processes that we can't specifically simulate, and then we evaluate the model. And these processes continue on, and there's interaction between them. But the one through line is that through each of these processes, we're using fundamental research and observations to step through these different aspects and develop the model. So, for example, for the top there, our core development of the model is maybe something like the basic Navier-Stokes equations and representing that and the equations of motion. But we also tell the model kind of some basic, hard, well-known facts about the climate, where oceans are, where lands are, and we can use observations to tell us that in really specific detail about what kind of land surface is occurring at a specific location. We tell our climate models about the makeup of the atmosphere, how much CO2 concentration there is at a given time and how that's changed over time. And so we use measurements from Mauna Loa, for example. And as you can imagine, NOAA does a lot of important observation work to get us a good picture of the composition of our atmosphere, which is really crucial for climate modeling, which we're now starting kind of to simulate in more detail, but at its core, this is information that we give to make sure that the model is simulating something that's realistic. And from there, obviously, we can say that CO2 hasn't changed at all and do kind of idealized simulations. And then once we have the basics, we start working on the things that we can't directly resolve and formulate parameters. So on the top there is a schematic of the complexity of a cloud. Right? These clouds occur well below the 25 to 100 kilometers that most climate models are operating on, and important processes about the clouds occur. Condensation, things like aggregation onto condensation nuclei, melting of ice into liquid, all affect the dynamics of clouds and ultimately actually affect the radiation you see at the top of the atmosphere. And so to develop these parameters, which basically are basic relationships between the bulk properties we can simulate directly, like humidity and temperature, and the finer processes we can't, like these cloud microphysical processes, we use observations, right? We can use CloudSat data of ice and liquid water content combined with data of temperature and humidity to understand those relationships and try to represent them in our model. But that alone is not really the end of how we use observations. You can imagine that we can come up with a number or equation for a certain cloud process using observations, but all those observations we used from CloudSat, for example, they have uncertainties themselves, right? So it's basically impossible to pinpoint a specific number. The parameter can be a range of different numbers. You need to choose one ultimately, but there's a range of realistic numbers that you could say agree with observations based on observational uncertainty. So a lot of times what we do is we take a bunch of these realistic parameter values and try a few of them in our climate model and see how it impacts climate variables we care about, which we also observe, right? So shown here on the left On the x-axis are model simulations with different configurations of different sets of model parameters, right? And what's plotted going up vertically and along the different rows are how those different sets of parameter choices, how accurately those sets of parameter choices lead to simulations that simulate these different variables. So, for example, in blue, excuse me, in purple, there are scenarios where the set of parameters chosen really accurately simulates those given variables compared to observations, root mean square errors of 20% or less. And in some of the darker colors, in red and orange, are scenarios where the different parameters we chosen are still quite inaccurate in some of these observed variables. And so you can imagine understanding the uncertainties in all these observations is really key, right? So not only can we use the uncertainties to figure out what range of parameters are realistic, but we can also use the uncertainties to figure out, once we choose a parameter, how close can we expect it to agree with observations. And these kind of details matter a lot during the model development process. Take a small subset of these different sets of parameters. The ones called drought rad, for example, represent different values for cloud droplet radius that you can put into the model. For something like surface wind, shown in the second row from the bottom, it doesn't really matter so much which one you choose. But for TLWP and TIWP, kind of total integrated liquid and ice water content, your choice matters a lot. And the uncertainty in our observations of cloud droplet radius have a direct impact on how well we can simulate kind of bulk climate variables that we really care about in the end. And the same thing, a lot of this kind of selection of parameters is tied to radiation and the energy budget. So it's shown on the right is trying to determine what's the best value in different models for a parameter representing the fall velocity of ice crystals, which is tied to the clouds and to radiation. And so the different colors are different models, and the goal essentially is to get your square and your diamond symbols within that gray band, which is observations of long wave and short wave radiation, plus and minus the observational uncertainty from the series instruments. And so, there's quite a bit of uncertainty in the observations. So a parameter value anywhere from 0.5 to 1.5 could be realistic and considered in agreement with the observations. And this range matters a lot. I mean, 1 watt per meter square difference in how you represent the imbalance can translate to a half a degree or 1.5 degrees Celsius difference in warming at the surface in the global mean. And so, I think another point worth mentioning is that as we scrutinize our models with observations in more detail, you can see a scenario where climate modeling is used to sort of inform our future satellite mission, right? We can say, for example, if we want to be able to simulate precipitation with X amount of accuracy, we need observations of cloud droplet radius of certain uncertainty threshold, and that can be used to sort of set the requirements of our instruments in terms of precision and accuracy. And so, sorry, I add vice versa, as the observations are being used to develop these parameters, but you can envision a scenario where this process of developing the parameters can also be used to help us prioritize what observations we need and how accurate we need them to be. So the final step is evaluation. This is where we start to look kind of in a broader sense at how the model is performing. So a GFDL I've been involved with NOAA's Model Diagnostic Task Force, a really neat tool where a climate model developer can run their simulation and quickly test it against observations of important processes. You can have a module that looks at how the simulation is representing MJO relative to observations, or how it's representing extratropical wave variations. We spend a lot of time evaluating trends in Earth radiation budget and how the model is performing relative to observation. So there's really kind of this hands-on interaction with the observation by the climate modeling developer, sort of doing the science in real time to understand what the model should look like and what improvements may be needed to get us there. And for that reason, there's this real need in the climate modeling community, not just for the observations themselves, but observations formatted in ways that scientists can use directly for analysis and to visualize the data as they step through their simulations and evaluate how they're performing over time. I think it's worth mentioning sort of another aspect of climate model evaluation is that we like to evaluate our models against other models. We do this a lot. Every handful of years, most of the world's modeling centers participate in what's known as the Climate Model Intercomparison Project. The last one was CNIP 6. And a lot of interesting findings emerged. One of them, which has persisted for decades, is that there's a lot of uncertainty and differences across models in how they represent what we call the equilibrium climate sensitivity, the amount of warming we can expect after a doubling of CO2. And recently there's been a big effort to use observations to try and constrain that uncertainty, pulling information from the present day instrumental record, from paleoclimates, using different emerging constraints as a way of trying to narrow down what is a realistic range of climate sensitivity values and seeing which models are probably unrealistic. And in this case, the assessment found that the models with some of the most extreme warming, the highest climate sensitivities, probably don't really agree with the best observations we have, which is probably a good thing. There's some really clear success stories using this approach of trying to understand the spread in our models and evaluate using observations which side of the spread is probably most realistic and which models are most realistic. There's a nice paper from a handful of years ago on the left showing the spread on the x-axis in the amount of absorption of solar energy for a given change in water vapor, which has a lot of spread across climate models and is really important for simulating global precipitation. And the study found that the models all clearly underrepresent that sensitivity relative to observations. And some of the climate modeling centers responded and updated their radiation codes to try and be more in line with the observations. So a really nice example of how we can use observations to kind of push modeling forward. It's not always that clear cut and doesn't always work out that nicely. I saw this firsthand in a paper we published a few years ago. We tried to, one important kind of fundamental aspect of climate modeling is the effect of changes in lapse rate and water vapor on the top of atmosphere energy balance, what we call lapse rate and water vapor feedbacks. And so the dots are different models, and I want you to focus on the x-axis there. You can see the spread in these feedbacks on interannual timescales, on timescales we can observe. And the vertical bars are observational and reanalysis estimates of that feedback from AIR satellite and from MERIT-2 and ERA-5 reanalysis. And the spread across those observational estimates is actually larger than the spread in the climate models, essentially making them useless for trying to constrain that overall model spread. And this happens from time to time. We may have multiple observations of the same variable, and in some cases from the same instrument, just using different techniques of retrieving those variables, and they can tell really different stories. So shown here are trends in temperature and water vapor by latitude and vertical level. At the top rows there are trends all from airs, just using different retrieval methods, and you can see that they paint kind of quite a different picture. So, we spend some time trying to understand this, and there's plenty of uncertainties on the observational side. But another factor is that when we compare these observations to models, at first it's not always kind of an apples to apples comparison. What we get from our observations and what the satellite sees is not exactly what we're simulating in our models, even for the same variable. So water vapor is kind of a really nice example of this. We get a lot of our water vapor information from the air's infrared sounder, which doesn't do well in the presence of clouds. So most of the retrievals of water vapor come from clear parts of the scenes that the satellite is observing. So in the schematic on the left, the light gray is where clouds are, and the dark gray is where clear skies are, and that's where the clear skies is where the water vapor information is mostly coming from. In a model grid, we get just one water vapor value, right? It becomes a grid mean value, and that grid has clear parts, and it may have cloud parts. And when we go to compare that against an observed water vapor that's been derived mostly from the clear part of the scene, it's not necessarily the same thing, right? We would expect, for example, that the water vapor inside a cloud is going to be larger, more moist than you would expect in a clear part of the scene where there's no clouds. So recently, a few of us have spent some time trying to represent that more specifically in the climate model and allow the climate model to compute a water vapor that occurs in the clear part of the scene and also in the cloudy part of the scene. And from there, we have the model take those two water vapors and run it through the radiation component so we can see how that impacts the model's representation of the top of the atmosphere imbalance and the overall climate system. So just as a kind of a neat example, we've done this in the GFDL model recently and tried to compare the simulated fluxes at the top of the atmosphere with observations in clear conditions. So at the top is observations of long wave radiation under clear scenes without clouds. The bottom left is the difference between our model simulation and those observations in the traditional configuration, where the climate model only sees that one kind of grid mean value, not differentiating between clear and cloud scenes. You get a bias of about -6.4 watts per meter squared, and you can see kind of a clear spatial structure to that. And on the right is our new scheme where the model is using a water vapor that's actually from a clear scene and therefore generating a radial flux at the top of the atmosphere that's truly more representative of what the model is observing, which is fluxes in a scene that's actually clear and not contaminated to some extent by the effects of clouds. And once we do that, the biases get reduced. They get reduced in the global mean, and they get reduced regionally. You can see some of the large biases in the open ocean start to get reduced. And I'll kind of just make the broader point that climate modeling in general, as we reach these higher resolutions and kind of reach towards unity with weather models, we're also starting to intertwine our climate modeling with observations more completely. and allowing the two sources of information to sort of feed off of each other. You may hear kind of buzzwords like digital twin being mentioned recently. And so as we do that, these efforts to think about not only the uncertainties of our observations, but what we're actually measuring, and making sure our climate models are simulating and outputting something that's analogous, those kind of activities become more and more important. And I'll sort of wrap up by saying I think that like, you know, this more intertwining of observations and the modeling is really a cool thing, and it brings more opportunity to use these models sort of in a more of an applications approach, a bit more operationally, maybe you can say, to really kind of fuse models with observations to understand what's going on with the climate and what'll happen into the future. You know, this becomes important as we start to approach things, for example, like Paris Accord deadlines, upcoming IPCC assessments, global stocktake. There's really a place for sort of this model observation fusion to tell us what exactly is happening with the climate system. You can imagine, along with NOAA's kind of climate dashboard of observations of greenhouse gases and Arctic sea ice, components from the model that give you a bit more detail that you can't really get from the observations alone. This is something I think about, again, for the top of atmosphere imbalance, which, as I mentioned, has been growing. You know, we can see from the observations that there's this really clear increase in the imbalance. But from the observations alone, it's a bit difficult to know exactly what's causing that, or what's causing some of these anomalies you see along the way, which can impact the climate as well. So you can take a model, and a group in GFDL did this recently, and run it with as realistic conditions as possible to simulate the observed climate as accurately as possible, and that's in the orange line and the orange shading there. Running the model with observations of sea surface temperatures and realistic changes in greenhouse gases and aerosols, and the model is able to recreate that series radial flux trend really nicely, shown in blue. So that's a good start. And then you can run the model again, but this time removing the human effects that cause those changes. Act as if the greenhouse gases haven't evolved or the aerosols haven't evolved, and that's what's shown in blue. And when you do that, you still simulate the changes in the radiation, but it's completely different than what we actually observe. You actually get a negative trend over time in the top of atmosphere radiation in that scenario. So this is sort of a way of telling us, using these idealized climate simulations, that what we're observing really couldn't have occurred unless humans were having an impact through anthropogenic effects. And so, you know, in the last handful of weeks, we've seen kind of headlines with the unbelievable warming we've seen globally. Things like scientists are baffled about why the oceans are warming so fast. Spikes in extreme heat are a mystery. And you can envision using observations and models to really try and respond to this and answer almost in real time what the causes of that warming is. Starting with observations of the total energy imbalance, breaking it down with observations into contributions from greenhouse gases and aerosols, responses due to changes in clouds and water vapor, to really understand sort of the science that's driving those changes. And then take a model to really delineate between what's naturally occurring and what's being driven by human activity. And so I'll jump ahead a bit. I want to make sure I leave some time for questions, and just leave you with some quick parting thoughts. I jumped a little too far. Let me share that again. Just to say, I think hopefully I kind of got across clearly that we use observations in climate model development throughout the entire process, from developing kind of the core basics and the input to evaluating the model, and along the way developing parameters for things we can't directly simulate. And it's really kind of a hands-on approach to analyzing the observations by the scientists. And so we use data in kind of gridded formats that we can easily compare to the model, and are continuously thinking of new ways to make sure that we're really having a fair comparison between the models and the observations. Um, and and through that process, we think a lot about uncertainty in the observations, along with uncertainty in our models, and grappling with things like, well, what's a realistic representation of a given process? And if we have to choose one, does it fall does it give us a climate that falls within the uncertainty range of what we actually observe? And as we think of this a bit more, I think there's a real path for using climate models to inform what kind of observations we'll need in the future. And with that, I'll take any questions. Thanks so much.
Thank you so much, Ryan. I know we are close on time, but I just wanted to say thank you, Ryan. This was excellent, and I know NOAA is the richer for having you join us. So welcome to NOAA, and thank you for for this excellent presentation. I just want to know, what are you working on currently, or what are you looking forward to working on as you continue your career with GFDL?
Yeah, so I think probably my big project right now is really trying to interrogate that trend in Earth's energy and budget I showed a few times, and bringing in satellite data from a few different instruments to understand sort of on a physical level what's driving those changes, not just long term, but really from year to year. I didn't get a chance to show it, but we're able to kind of pull out the signal that's due to changes in aerosols, for example, and see how that's impacting the radiation over different regions, given how we try to improve air quality in certain places versus others. And so I'm working on that from the observational perspective at first, and then the hope is to kind of layer that with models and being able to translate that into understanding what components we have specific details about the components that we can't directly observe, and how those specific components lead to given amount of temperature change or change in precipitation, so on and so forth. So I'm really interested in this idea of kind of combining observations in the models to teach us something about what's going on with the climate.
Perfect. I know we are right up on time, and I know you skipped some slides, so we might have to have you back to,
That sounds
finish
good.
those off and to tell us more.
Sure.
I'm going to echo what I see in the question panel or in the comments, which is this was a wonderful presentation. So I want to thank everyone for joining us, and I hope everyone has a great day. Thank you again, Ryan.
Sure, anytime. If you're in the Silver Spring area, come meet me, guys. Thank you so much.